Baltimore was a furnace. Firefighters had arrived from other cities with engines, crews, pumps, and long coils of hose. The hydrants were already there. But when one visiting firefighter tried to connect his hose to a Baltimore hydrant, the metal coupling would not screw on. The diameter was a near match. But the threads? They wouldn't bite. He jammed the coupling on, twisted with all his might, and nothing. It just wouldn't lock. He tried again. The coupling turned slightly, caught against the metal, and stopped. A second crew scrambled forward, dragging a heavy New York line, then a third from Washington. One by one, the metallic clangs of rejection echoed through the smoke. None of them fit. The crews had crossed miles to reach the fire. Their equipment failed in the final inch. In 1904, the Great Baltimore Fire revealed a deadly secret: even 1,000 heroes are useless if their tools don't speak the same language. To understand how the city reached this breaking point, we have to look back to how it started, a quiet Sunday morning, February 7th, inside the Hearst building. Fire engines arrived quickly. But the heat triggered an explosion of dry goods stored inside, showering neighboring buildings with embers and spreading the flames within minutes. Driven by wind, the fire moved through the financial district and toward the docks. What began as one burning building became a moving wall of heat, smoke, and collapsing structures. The fire burned for around 30 hours and destroyed more than 1,500 buildings across dozens of city blocks. The mismatched hoses did not start the fire. They were not the only reason it spread. But they weakened the exact moment when help from outside Baltimore was supposed to change the outcome. As local firefighters became overwhelmed, companies rushed toward Baltimore. From New York to Washington, fire crews from across the East Coast were racing toward the smoke. The reinforcements brought more people. More engines. More pumps. More hose. Hope arrived on the tracks, train after train of reinforcements from across the East Coast. It looked like the cavalry had come to save Baltimore. But that hope was about to vanish in the final inch of a brass fitting. A fire too large for one city would be fought by several cities together. Help had arrived. Then the visiting crews reached Baltimore's hydrants. Some of their couplings were too large. Others were too small. Some appeared to match in diameter, but the spacing and shape of the threads were different. A hose that saved lives in Philadelphia was nothing more than a heavy coil of rubber once it crossed into Baltimore. Many visiting crews had reached the fire. But their equipment could not reliably reach the water. Not every visiting firefighter was completely helpless. Some crews bypassed the hydrants entirely, dropping suction pipes directly into the harbor or using wet burlap to wrap leaking, mismatched connections. This incompatibility was the friction that turned a local fire into an unstoppable catastrophe. But many engines were hampered or sidelined precisely when Baltimore needed every available stream of water. The strange part was that nothing was necessarily broken. Baltimore's hydrants worked. The visiting hoses worked. Each system performed exactly as intended inside the city that owned it. The disaster wasn't a lack of water or a lack of men. It was a silent, invisible wall built by 1,000 different designs, finally crashing down when the world needed them to be one. America did not yet have one firefighting network. It had hundreds of local networks that happened to perform the same job. Baltimore used one mechanical language. Philadelphia used another. New York might use another still. Inside each city, this did not look like a serious problem. A fire department purchased hoses that matched its own engines and hydrants. When old equipment wore out, it bought replacements that matched everything it already owned. That was practical. Replacing thousands of working connections simply because another city used a different design would have been expensive. And as long as each department mostly fought fires inside its own boundaries, incompatibility remained easy to ignore. The problem became visible only during the worst possible moment. The people arriving to save you were using someone else's equipment. That is what made the Baltimore fire more than a local disaster. It exposed a weakness hidden inside the way American cities had developed. Every city had independently answered the same basic question: how should a fire hose connect to water? And America had produced hundreds of different answers. After the fire highlighted the problem, the National Bureau of Standards, now known as NIST, began a massive survey of every hose coupling in the country. What they found was a mechanical nightmare: over 600 different, incompatible sizes. 600 ways to fail when a city is burning. More than 600 answers to one very simple question. Some couplings differed in diameter. Some used different thread spacing. Others used different shapes or dimensions. Many were probably reasonable designs on their own. But a connection does not succeed simply because both pieces are well designed. It succeeds because both pieces agree. This is the purpose of a technical standard. A standard is not necessarily the single perfect design chosen from every possible option. It is a shared promise. This thread will have the same shape. This connector will have the same diameter. This fitting will work even when the people using it have never met before. Using information gathered through the federal investigation, fire protection organizations selected a common design for hose couplings and adapters. In 1905, the National Fire Protection Association adopted its first standard for fire hose connections. The idea was simple: a crew arriving from another city should not need to know who manufactured the hydrant. The hose should connect. The water should flow. The firefighters should be able to begin working. But creating a standard did not instantly standardize the country. Cities still own thousands of hydrants, pumps, engines, and hoses built around older designs. Replacing equipment that still worked cost money. Local governments controlled their own water and firefighting systems. Departments had years of experience with the connections they already used. Manufacturers had customers invested in existing designs. A document could declare a national standard in 1905. It could not make every old hydrant disappear in 1906. Adapters provided one bridge between old and new systems. They allowed equipment using one connection to communicate with another, almost like an interpreter placed between two mechanical languages. But adoption remained slow and uneven. By 1914, federal reports admitted that while everyone understood the solution, a lack of coordination was still stalling progress. But progress moved at the speed of budgets and bureaucracy. The old threads proved difficult to erase. Even a century after the Baltimore Fire, in 2004, researchers found the work unfinished when they checked 48 major cities. The result? Only 18 had fully adopted the national standard. In the other 30, the same mechanical language barrier remains, ready to complicate a modern rescue. That figure describes the cities surveyed in 2004, not every hydrant in America today. But it reveals something important. A disaster can make the solution obvious. It cannot make adoption automatic. Every standard must compete with the enormous weight of things that already exist. Old machines. Old contracts. Old budgets. Old habits. A city may agree that a new design is better and still be unable or unwilling to replace every functioning piece of the old system immediately. That is why modern life is filled with adapters. They are small translators between systems built before everyone agreed on a shared language. Fire hoses are only one example. Standards quietly determine whether a plug enters a socket. Whether a shipping container can move from a ship to a train and then onto a truck. Whether two pieces of communication equipment can exchange information. And whether emergency teams from different jurisdictions can share the same source of water without stopping to solve a mechanical puzzle. When standards work, the connection is uneventful. The plug enters. The container fits. The device connects. The hose screws onto the hydrant. Nothing remarkable happens. And that is precisely the point. Standards are difficult to notice because their greatest achievement is preventing a problem from appearing. The firefighters who came to Baltimore had courage. They had engines. They had crews. They had hoses. And the city had water. What many of them did not have was an agreement about how those things should connect. The Great Baltimore Fire did not prove that Baltimore's hardware was broken, it proved that a system designed to work in isolation is a liability during a catastrophe. It proved that emergency systems cannot be designed as though they will always work alone. A local system may function perfectly for years. But disasters do not respect city boundaries. And when help crosses one of those boundaries, compatibility becomes part of the rescue. Standards are easy to ignore because, when they work, nothing dramatic happens. Next time you see a fire hydrant, look at the threads. You're looking at a silent promise,